So very good afternoon to all the participants here, as well as the eminent speaker of the session, Dr. Akhilesh Mohan here from IT Kharagpur. I welcome you all in the 11th technical session of this technical online FTP on system engineering on topic advances in IoT, sponsored by AICT Training and Learning Atal Academy here. So in this session, we will have a very informative session with the sirs here on his research experience on this topic, as well as his learnings as a working experience here. So before I would invite the sir here to take over this session, I would like to give a brief bio of the sir here with all the participants here. Mohan sir is an associate professor in electronics and electrical engineering department here in IIT Kharagpur here, and sir has worked in IIT Kharagpur in from 2013 onwards to till date here. Initially was associated as a assistant professor here, later on has been promoted to the associate. And prior to that, sir was associated during the span of 2011 to 13 in IIT Jodhpur as an assistant professor. And before that, he was working as a scientist in the SAC, ISRO Ahmedabad Center here in 2009 to 11. Time is running. PhD and MTech here from IIT Kanpur, and he has completed his BTech from KNIT Sultanpur here. So, sir's present research area include about RF and microwave circuits, antennas, array, microwave filter, UWB antennas and filters, metamaterials, and sir has a vast experience in the research area here, and it could be reflected from the kinds of projects and the number of projects he has handled here. So at present, two ongoing projects is under the supervision of sir here. So one is a low frequency, flexible, and conformal capacitive surface-based broadband absorber with minimum thickness and maximum bandwidth targeting surveillance radar signal avoidance, sponsored by the Science and Engineering Research Board, SERB. Another project is on design and development of substrate integrated waveguide SIW based bandpass here, sponsored by the KCSTC IIT Kharagpur here. And before that, Sir has completed a few projects here as a PI as well as a co-PI here. So PI has completed the project here on design and development of compact multi-band UW MIMO antenna with WLAN band notch functions, sponsored by Science Engineering Research Board. Another project completed on the design of miniaturized antenna for UWB technology, SRIC, IIT Kharagpur. Another project he has handled here on the feasibility of design and development of L and S band dual polarized staired common aperture microstrip antenna, sponsored by KCSTC IIT Kharagpur here. He also completed one project as a co-PI here on development of substrate integrated waveguide SIW based passive devices for satellite transponder KCSTC. Here, sir is very active in the research domain here. In the last few years span of his academic career, he has published more than 54 journal papers in all the reputed journals here. He has published more than 29 papers in conferences associated with one book chapter, and his citation work of his publication is more than 1,000 here. Sir has also submitted patents here, three patents. The one is on a millimeter wave horn antenna, along with S. Chaudhary here, the D. Guha here in 2018. Another patent is on a substrate integrated waveguide inspired multi-horn antenna with the same research group. Another patent on the substrate integrated waveguide monopole antenna, along with S. Chaudhary here in 2016 here. At present, 6 PhD students has completed under the sir supervision, and 5 PhD students are ongoing here. I'd like to share with you all here that I am also one of the students who has completed PhD under the sir supervision here. So if you remember the previous sessions here, I have introduced one of my co-supervisor, Dr. Sandeep Yadav, IIT Kharagpur here, and I has also an opportunity to work under sir's guidance here, so mainly here on the UWB antenna aspects here under supervision at IT Kharagpur here. Sir is a very active member of IEEE activities here. So with this, now I request the sir here to, to initiate this technical session here with the participants here. Now, sir, please.
Okay, thank you, Sri Vishal. So you've given a very long biography, explanation that was not required. Okay, thank you for that. So let us start with our session. That is massive MIMO antennas. So I will share my screen. So is my screen visible?
Yes, sir. It is
okay. Okay, so I will be using, let's say wherever, so this is my screen, so I will be using whiteboard wherever it is required. It is whiteboard, so I will be using. So let us start with that one. So massive MIMO antennas. So I will, okay, let me switch off my camera to save the bandwidth. Okay. Okay, no problems. Let it be there. Sorry. So let us start with the massive MIMO. So massive MIMO antennas. So massive MIMO technology has not been explored much. So I will just discuss the massive MIMO. What is massive MIMO and what are the massive MIMO antennas which has been designed for the massive MIMO applications. So here is the introduction of my talk. So first I will present this is introduction to 5G technology. Then what is massive MIMO I will present. Then I will present what are multi-beam antennas. In multi-beam antennas, it can be classified as passive multi-beam antennas and active multi-beam antennas, that is multi-beam phased array antennas. And finally, I will give you some of the examples of the MIMO antenna. Some of the examples of the MIMO antenna I will give you. Okay, Shivshal, can you switch off my video?
Yes, it could be done, sir. It can be done, sir. Okay.
Okay, let
I
me
think
stop.
it is stopped, sir.
Yeah.
Yes,
Okay.
Yes, it is stopped, sir.
It is stopped. Okay. So now. Okay. So we will, and finally I will conclude my talk. So this is introduction. So introduction as long has been, so this is the 11th session, technical session. So much has been said to the 5G technology. 5G technology, which will be the basic for the IoT applications, where the millions of devices will be communicating through each other. So what are some of the technical terms related to the 5G technologies? They require data rate from 0.1 to 1 Gbps and connection density of 1 million subscribers per kilometer square. Latencies should be very low. And these are some of the technical details of the 5G technology. Now the question comes, how to implement it? So let's say they have given this, I want this one, I want this. But how to implement it? That is very challenging. So how to do that? So there are several technologies which enables us to accept that challenge. One is ultra dense network, another is novel multiple access. People are working on that. Then all spectrum access, massive MIMO, millimeter wave communication, semiconductor technologies, antenna array beamforming, and full duplex. So full duplex or flexible duplex communication. So you can see this can be broadly divided into 3-4 categories. One is computer, that is networking aspect, another is access, that multiple access, there, and then massive MIMO, this, then semiconductor technology. So it is not like that only one can achieve it. So it can be mutual, it can be collective way of all the engineers and scientists to work upon it. Okay, so now since I am an RF engineer or RF that is linked with the electromagnetic domain, so we can have the what other. So I have sort out the subset from the whatever this group of technologies required. That is millimeter wave communication, where you can have millimeter wave communication, where you can have, so the devices will be very small in the millimeter wave communication. We cannot go for the lower frequencies because devices will be very big in size. It is linked with the lambda. Then massive MIMO, which I will be discussing. Then antenna array beamforming is how to do the beamforming, and full duplex communication. Full duplex communication means you need to transmit and the receive at the same frequency. And there the multiple access, different types of access has to be introduced, and there should be very good isolation between the transmitter and the receiver. These are some of the technologies or some of the things which are linked with the EM perspective, that is electromagnetic perspective. Now, so before moving further, let us divide all this. So it was started long back, maybe 4 or 5 years back. What are the frequencies we have to use for the 5G communication? So the ITU and FCC, that is International Telecommunication Union, and the Federal Communication Commission has decided to work on these frequencies. That is 3.4 to 3.6 gigahertz, 5 to 6 gigahertz. These are the sub 6 gigahertz. People are working on this one. And apart from that, so, and these two first frequencies are for the indoor 5G communication, means for shorter distance communication. But so for long distance communication. And apart from that, higher frequencies, that is millimeter wave frequencies, that is 24, 37, and 66. These are for the indoor communications because they cannot propagate. They cannot propagate for the longer distance. So now the researchers has begun. Now it is still in the nascent stage. People are trying to design the base stations, modules, and the mobile phones. For that, you can find out the mobile phones which are easily available. And in some countries, the 5G is also introduced. Okay, so now, so in our presentation, what I will be discussing, I will be presenting some of the designs which will be based on the indoor 5G applications and outdoor 5G applications, both the things. Okay, now here are some of the challenges for the millimeter. Okay, so here are some of the challenges. So EM, let's say at millimeter wave frequencies, it suffers more free losses and blockage because it cannot penetrate to the building or any object. So it will have that is signal to interference plus noise ratio, that is SNR. Instead of SNR, we define SINR, that is signal to interference plus noise. And so what for that we require the high directional antennas. So the beam should be directional, because if it is not directional, then we will have it will loses its SNR, so it will have more interference noises. So for that, the line of sight of communications are required. But if you have a line of sight communication, that is LOS link, then it will be only limited spatial coverage. It not be used for multi-user communication. So you have to be in this specific location where you will not have any object, any building or anything. But that was undesired. So that was undesired. So now for long non-line of sight communication, a single beam needs to be steered. Means, let's say if you move from one position to one position, so you need to a beam steering. Either it can be beamed mechanically or electronically to find out the substitutable, that is reliable link, so that your communication can occur. So how we can do that? That cannot be done by a single antenna, which will be having a directional beam. So to achieve that, the multi-beam antenna, the concept of multiple antenna has been proposed. That is the possible solution. So there, what is multi-beam antenna? So as you can see from here, the base station is there. So this base station emits different types of, different narrow beams, the beams which will have the narrow bandwidth. So a narrow bandwidth, and all the users can communicate from here. So it can be said that it will be capable of generating concurrent but independent directive beam. Independent means the beam of one user should not interact with the other. Maybe there will be some interaction, but it should be as small as possible. So there will be some threshold value, and with a high gain to cover a predefined angular region. Let us say that if you have a base station, so if you want to cover the whole entire 360-degree, then for each angular separation, you must have a single directive beam. So how to achieve that? So the MBA serves as a key hardware for enabling your massive MIMO technology, that is multi-beam antenna. So what is massive beam antenna? So what we can have? So here I have shown you here. It is having a numerous antenna. It is called massive MIMO. Basically, what I will say, this massive MIMO is a misnomer. It is nothing to do with the MIMO technology. It is a misnomer. It is basically a multi-beam antenna. So you need to have a multi-beam antenna, where in the conventional MIMO technology, you have all the independent antennas are rotating separately, and they can increase the channel capacity. They can increase to overcome the multipath fading. So this is the concept used in the conventional MIMO technology. But here in massive MIMO, it has nothing to do with this MIMO technology. So here you have a number of sets of antennas which are mounted on the base station. So you can have you can vertically move your beam or horizontally do, that is either in the elevation plane or in the horizontal plane. You can move the plane. Basic thing is that you have to cover the entire area or entire region. So it utilizes a large number of antennas which can be coherently and adaptively. Means, let's say if I want a beam at certain position, so I will have different type of, I will feed my antenna with different at one port one. If it requires different another beam, I will feed at different ports. So it is very important to fully coherent and adaptively. And also it will have a orthogonal beams which should possess the higher angular selectivity. So then you will not have any interaction between the beam. So isolation will be very high, and so it allows us the frequency to use. So if you are using for one frequency, you can use that frequency maybe at another angle. You can use that frequency at another angle, which will give you higher system capacity. Okay. So now the multi-beam antenna. So I will be focusing on multi-beam antennas, which is the basic of your massive MIMO. So the multi-beam antennas was not new. It was started long back. Its history is that. So it was primarily used for the radars and satellite communications. So, but there it was having the very bulky. They are using something like they are using like waveguide based horn and waveguide based antennas, or maybe pyramidal, that is parabolic horn. They are excited by the horn antennas. So they are using. So they are physically bulky and expensive. Now the advantage of if you use for the millimeter wave frequencies or at compared to sub 6 gigahertz, the wavelength is very small. Your component will be very small. So you can achieve higher array gain in the same area or the same compact area. Okay, now and so you can use, or the multiple users can be incorporated there. Okay, so now okay, and also so it uses basically spatial rich channel information which can be exploited to the fact that narrow beams emitting into different directions will undergo uncorrelated multipath channels, and it will be a beam space. It will improve your link reliability and reduce the outrage probability. This was one of the feature of your, that is latency should be very small, so outrage probability should be also very small. So your link will be always available. To achieve that, so what you have, so the multi-beam antennas are a promising candidates for both for the base stations and the user terminal for the 5G to enable the dynamic and reliable wireless link for high-speed data communication. So now after that, once it was proposed, so now researchers tries to dig upon the fundamental theory, how to achieve that, what are the architecture and how to implement it. regarding the what the component should be designed, what component we should use, and how to achieve the miniaturized version of it. So here I have shown you some of the antennas which are used for 5G base stations. This they have proposed in the literature. Here, the first design, they have used an array of patch antenna. So it was something like hexagon, something like a square shape. So they have mounted one upon each, such a way that way they can have the narrow beams in all the direction. In this is 360, that is in the omnidirectional plane. And this is also one of the, that is 28Q. I will discuss the second one. So here also, that is 28 port cube based massive MIMO antenna. So where they have used, and it can also radiate in the all the directions. Okay. Here they have used patch antennas, and here they have used Vivaldi and the patch antenna, combination of both the end fire and the antenna elements which have the end fire radiation and the broadside radiations. Okay. Now regarding the antenna for the 5G user terminals for the mobile applications. So it can be either 8-port antenna or it can be either 16 port. So I have shown you here the 16 port antenna. It can be, so to communicate with the base antenna, so you need to excite your antenna in such a way that it will receive the desired beam from the base station. And similarly here also, this is just to show you how it will communicate, what are the radiation pattern it will have. So here just to take it from the internet. Okay. Now, so this multi-beam antenna can be broadly classified into two categories. First is passive multi-beam antennas, and another is multi-beam passive active, and passive multi-beam antennas or active multi-beam antennas, or it is also called multi-beam phased array antennas. So now, so the passive multi-beam antennas doesn't use any active component. It will be just you have to feed this one. It will have numerous ports. You have to feed, let's say it will have n number of ports. If you feed port 1, you will get one beam. If you feed port 2, you will get another beam, and so on. But here in the active multi-beam antennas, it will be having, it uses the phased array antennas so you can switch your beam by using different phase shifters, and basically you can electronically tune your beams. So what I will be discussing here, the passive multi-beam antennas. So passive multi-beam antennas can be broadly further classified into based on the reflectors, lenses, and beam-forming networks. So I will discuss all these three in details. And while the active multi-beam antennas can be, MBS can be classified, multi-beam antennas can be classified using the passive and the active. So both of them will have active and passive components. But here so I will discuss why it is called passive multi-beam antenna arrays. So it uses some passive components for switching. That is why it is called passive. Okay, now, so it is the passive multi-beam antenna, that is PBMA, PBMAs. So it is we can achieve the desired beam forming in the RF domain without using any active component. We will not use any active component. And here, as I said, it will use numerous ports. That is finite number of ports will well isolated inputs. This all the ports will be isolated to each other, and each port will be connected to either transmitter or receiver, which controls your single narrow beam which is pointing to a predefined location. Okay, now so it can share, means it can be simultaneously emitted from the shared aperture. Means we have the same aperture, only only the feed has to be different. Okay, so feed is too different, and and the resolution is limited by the beam width. So, and it depends on the number of beams you want, which you want to cover with 10 beams, you want to cover into 8 beams. So you require, if you want to cover in the 10 beams, you require 10 ports. If you want to cover into 20 beams, you require 20 ports for this passive multi-beam antennas. So it can be characterized by its scanning range, polarization. What is the polarization do you want? You want dual polarization or single polarization, linear, or you want linear polarization? Then linear polarization is preferred. Okay, now, and you want, what are the gain you want, what are the side lobes you want, bandwidth, port isolation, and efficiency. These are some of the things. Now, based on that, we can, as I told you, the architecture and the principle of operation, we can broadly classify into 3 categories: reflectors, lenses, and beam forming circuits. let us start with the lens that is reflectors. So it is the reflector based PBMA, that is beam forming antennas. It uses the reflector based quasi optics with continuous aperture, whose operation can be really understood from the ray optics point of view. So it is basically, it is performing the Fourier transform in redistributing energy into the different means it is basically redistributing its energy into the free space wave to the required aperture distribution. For example, the requirements are, it is, you need a reflector, that is the parabolic reflector, and you need several antennas which is needed to excite this reflector. So, and apart from that, transmitter and receivers are required. And so this, if I feed port 1, so I will have this blue color beam. If I feed, and all these antennas needs to be placed near the focal point of your reflector. So you need multiple feeding antennas which are separated at a distance d from the, which are distance d to achieve the good isolation between them. Okay. So now, and feeds to be located at the focal point. So what are the key means what is the angular beam, what is the angle of separation of, that is, what is the beam width we require, and what is the cross coupling? It determines by the f by d ratio of this reflector and the distance d between the antennas. So they governs basically the beam separation, and they miss what is the beam separation between the two beams, and what is the cross coupling between the adjacent beams, and what is the spillover of the reflector, and what is the polarization degradation caused by the mutual couplings of the feed antenna. So these things are required. These things decides the antenna radiation characteristics. Okay. So now you can modify your radiation characteristics by modifying the shape of the radiator. So you can, if you modify the shape of the radiator instead of having or you adjusting the feed or optimize the orientation, means you make it offset, you will get different beam. You can, this basic thing is that you have a control over your beam by these parameters, by modifying the shape of the reflector or adjusting the feeding element, optimizing the antenna, optimizing the orientation, and positioning the reflector and the feeds. Okay. Now here it was proposed in the, that is offset feed reflectors, where the let's say, so you will not get, if you see the port 2, the port 2 is radiating here, so it will have some blockage due to the feeding arrangement. So it was overcome by offset fed reflectors for the multi-beam antenna system. If you use offset with parabolic reflector, then you can overcome the blockage which was caused by the feeding. Okay. Now generally it was used for it was used in the earlier days also, that is, it was horn antennas were used for the feeding, which have the high core polarization level and side lobe levels. So which can be, so it was, the system was very bulky. Means if you use horn antenna, it was very bulky. Now to improve that, so where different types of feeding arrangements are there, so they have replaced this horn antenna with the different printed radiating elements like patch antenna or an antenna array or leaky wave slot array, electromagnetic EBG based antennas, and some modified hard or soft antennas which uses the metamaterials. So these novel feeding arrangements or novel feeding elements will improve their cross polarization level, and then you will have higher pressure efficiency. Means whatever power you are feeding, so it is not going into the another cross pole, so it will be radiating with the copole, and it will have lower mutual coupling and low profile. Low profile is also very important. Low profile means its thickness should be small. So if you use horn antenna, it will be having larger thickness, which was undesired for the compact application, is for the applications. Now, so earlier, so what they have did, so they have replaced this metallic dish with a wired mesh. So, but wired mesh without sacrificing the multi-beam performance. Multi-beam performance was not sacrificed. After that, what do we do with the advent of the PCB technology? So they have replaced this reflector with the planar reflector. So they call it as a planar reflector arrays. Planar reflector arrays, and these are they means we replace this conventional curved surface with the planar reflector arrays to have the low profile, low cost, and lighter weight components can be used. Okay, now reflector. So what is reflector based array? The planar reflector is comprised of solid metallic plane or which contains a single or multi-layered antenna arrays printed at or. So here you will have on the array you have a resonant scatterer. It has to be optimized with the size and pattern and dielectric. So here instead of having this reflector, so I will use a, earlier it was a parabolic reflector. I have replaced with a thin planar reflector which uses the resonant based scatterers to get the beam. And also here you can use the all the concept will remain same. Instead of just we have replaced the reflector, so you can use the center fed reflector or offset fed reflector to produce a multi beam or single beam or for use for single frequency or multiple frequency. It has been demonstrated for the millimeter wave frequency. So now this was to further reduce the size. So it was shown, just I have shown you here. So they have used something like folded reflect array. So where they have used something folded, and here it can be seen here. So it can be seen. So if we feed from feed 1, 2, and 3, so I will have different feed beams. So it was designed for that is 77 gigahertz radar. So it is something like this. So they are on the top. This was the feeding arrangement, and on the top they have a reflect array, folded reflector. Now this was folded reflect array. This was concept behind. Now another is they want to use we can use it by using lenses. So lenses can be used for beam forming for the transmitting device. It cannot be used for the receiver. It is used only for the transmitter, which provides the targeted multi-beam radiations. So a beam that is the typical lens should have a continuous aperture. It does the same thing, that is Fourier transformation. Fourier series transformation. So now your lens is illuminated by this multiple antennas here, and because of this profile of this lens, it will generate the beams in different directions. Again the same, and so the problem of the blockage which was present, which was overcome by the offset feed, so it was overcome here by using the lens conventional homogeneous lens shaped structure. Now, so lens can be either concave or convex in nature, and they can be derived from the different isotopic material. It can be shaped, bifocal, spherical, different types of lenses are there. So main aim is to, by using this type of lens, we have to increase the gain and reduce the side level of our and increase the gain, so that we must have the pointed beam. We must have a very narrow beam, which is our desire, which is required. Now, based on that, different types of lenses were proposed. That was conventional. Once they have used this gradient based. So here, instead of having the homogeneous dielectric, it was having some conventional Lundberg lens. So it was having the lens was direct, is having the graded index. Means it was having higher density at the center, higher dielectric constant at the center, and as the periphery. Basic thing is that we have to create the lens action, and from lens action we will have multiple beams. Similarly, they have Maxwell's fish eye based links. So it is something like, it is since it is an entire spherical in shape, so it was some size will be reduced here. So we have the gradient based half Maxwell's fish eye shape links. Just to tell you, all these things were reported in the optics domain. Now, so what again I will tell you, this is instead of directly radiating from the lens aperture, the output ports means instead of directly we are radiating from this lens aperture, we will connect this output to the another antenna array or sub array. So what we can have, then we can have multiple types of multiple types of antenna beams. So this was reported in the literature. So people have designed using the different types of here. These are some of the conventional, or this is three-dimensional lenses. Now instead of connecting, so instead of radiating from there, we will connect this lens to the an antenna array. So it will increase its efficiency and beam width will be narrow. So that we have the rules lens, Rotman lens, and RKR lens. So RKR, this lens R2R provides 360-degree azimuthal coverage, and this radiator can be either patch or slot or leaky wave antennas can be applied. So this was demonstrated for the satellite communication and the automotive application, but not still it is not done for the massive MIMO application, for the 5G applications. So they did it for the satellite communication. So as was what I was told you, so here it is something like a Rotman lens. So they have different feeding point and this Rotman lens, and after once instead of having this lens here, so what they are connected, each of the feed is connected to the each part of the lens is connected to the one SIW based antenna array, and it will radiate in the different directions. So you can have, here it was shown, you can have the seven different beams at different angular separations. It can be achieved. Similarly, this was a Rotman lens. This was very popularly used for in the literature. If you see in the literature, it is very popularly used. Now, another is your KR2R. So it will have there here we have in the Rotman lens we have only seven beams can be achieved. But here, if you see, the beams are not uniform. Means you have the beam, some center beam is having the larger this one and is higher gain, but the other gain, it is normalized gain. Center beam having larger gain, and other gains as you move away from the center, your gain will reduce. So now, but to overcome that problem, to have more number of beams, they have come up with the RKR lens, where they have overcome some of the problem of the gain reduction at the, if you move away from the central point 0 degree, and you can have the more number of beams. So it has a lesser gain variation compared to here. If you see, you have gain variation of 5 dB. Here it uses the same thing. It uses something like KR lens, and after that it is connected to the SIW based antenna arrays, which will generate the different beams. Okay. Now, so we have seen the reflect arrays. Similar to the reflect arrays, we can have the transmit arrays. Transmit arrays. So transmit arrays are like, it's tough. We will not have the we will not have this one ground at the back. We will have the transmit array will have the phase shifter, or it will be just a transmitting there. Okay, transmitting. So now, so it will also, so it will have the phase, it will require the required phase delay can be achieved by using the printed metallic resonator or by inserting between the lenses. I will explain this massive MIMO transmit array in detail later on. How does this one work? So we will have, instead of having the scatterer, so here the scatterers will be there. So they will have each of, let us say that at the center it requires lesser phase variation, but as you move away from the center it requires larger phase variation. So we have to arrange this scatterer in such a way that each of the antenna when excited will impinge the electromagnetic wave, and it will have the numerous variations. It will have the numerous variations. It will have some systematic variations, so that you can multi-beam can be generated. So it was shown here. So I will discuss in detail. So Jerusalem cross wave. So this was their antenna, that was something like patch antenna was there, and they are connected to the 8 ports, and there we have something like a transmit array. Transmit scatterers were there. So they are able to achieve the similar characteristics with the water, and the problem of blockage was solved here, and it can achieve larger gain and lesser gain variation also with respect to angles. I will discuss in detail this one. And so we have discussed about the reflect arrays. We have discussed about the what are the things? Lenses and the deflectors. Another is beam forming. You can use beam forming network to design the that is multi-beam antenna arrays. So what is beam forming network? So it uses, instead of providing the phase shift by the curvature profile of your reflector or by you having the transmit array, we use the transmission lines and the directional coupler. Means the signal will pass through this one. Earlier the electromagnetic wave was placed at the at some distance d, such that electromagnetic waves when impinges, so they will scatter and it will have similar multi-beam behavior. Okay, now so it again depends. Since it is again a passive beam. We are discussing the passive multi-beam formation. So number of antennas determine the number of resolutions. So that is the number of ports. If you have more number of ports, you will have better selectivity. And okay, so for that, the popular approaches are, they use the Butler matrix and the Blast matrix. The Butler matrix, so the simpler Butler matrix, they use something like HAB. So typical beam forming N cross M Butler matrix consists of a fixed phase shifters and 90-degree hybrid couplers, which can produce N orthogonal beams radiated from a uniform linear array. Means, so this is okay. So if I feed port 1, so this all the antenna elements interact in such a way that I will have, I will feed all the, so I will have the multi-beam radiation. So for that I require an additional hardware, that is 90-degree hybrids, and the fixed phase shifters are required, and fixed phase shifters are desired. Now, but the disadvantage is that, so here you can, so yeah, so okay, yeah, so you can have, so since if you see the, I have not shown the layout. If you see the layout is very complicated, and since the signal is passing through your components, you will have more increased losses. So for that, so to control, you have losses, and to control the side lobe level and the crossover of the beams, various modified versions of the Butler matrix have been proposed. Like they have used amplitude trap ring and different others has been proposed, if you see in the literature. Apart from that, so Butler matrices, so antennas the antennas can be used. You can use the microstrip feed, or you can use this plot line. The different types of antennas can be used for this one. But popularly the SIW based is used, because the SIW is it is a planar in structure and it has low loss properties. So it was shown here. So it is something like, that is 4x8 Butler matrix. So here the 4 ports are there. So we are able to generate these 8 antenna arrays here. The 8 antenna longitudinal slot antennas are there, which can combine to give us 4 beams, which covers the whatever this azimuth angles as shown here. So here the losses, if you use SIW technology, the losses will be very small. So everything we have implemented. You can implement the hybrids, you can implement the phase shifter, the SIW technology. So you need not to have the integration of problem with the integration of components. So it can be designed on the same board itself to have the Butler matrix based beam forming network. So people have designed it. And so now another is Blast matrix based, so which uses so it is more flexible than the Butler matrix. It uses which allows in generating an arbitrary number of beams, each beam pointing at arbitrary position, even and with distinct pattern. Means here it is not like that. In the Butler matrix, beam should be similar. Means if you have a narrow beam, means you can have all the beams should be of the same time. But here you can have some beam can be narrow, some beam can be wide. You can achieve these things. So here traveling wave feed lines can be used to generate the N beams here. Okay, so here it was shown here, just to that is a double layer. Again, it uses the SIW technology, that is 4x16 Butler, that is Blast matrix realized by the SIW structure, which we can have the 4 beams with the angular separation of 30 degree and gain of 90, that is gain of 30.5 dB with a beam crossover level of -9 dB. Just to tell you about this one. Okay, now this was the multi-beam antennas. So now that was based on the passive components. Now we will get back to the active means which uses the active component. I will not discuss into the detail, just I will give you to brief overview of that. So the passive multi-beam antennas have the fixed beams, but you have to, and it is linked with the poles, but you cannot, so once the system is manufactured, you cannot have any frequency beam adjustability, means you cannot vary your beam. So for that, the phased array antennas were popularly used, that is frequency, that is they have the beam adjustability. You can tune your beam depending upon your mechanical and electronic tunes. So it was proposed long back in 1950s. It was popularly used in the military and commercial radar applications and satellite applications and for the imaging applications. So it originated from the phased array antennas. So now people have tried to apply that concept, but there, whatever the electronic scanned array, there we have only a single beam. But what we want for the massive MIMO, we want multiple concurrent beams using the phased array, which was developed to target for the multi-user applications, and also frequency can be reused. So it was again decided classified to the two, that is passive multi-beam phased array antennas and active multi-beam phased array antennas. So the difference between these two, so it uses some digital signal processing, and the difference between these two. So what do you do? So here, so in the passive multi-beam phased array antennas, so what we have, so we will have the passive components here, antennas, and this one, antenna. So we have signal processing, means it will be signal processing will be done at the base, at the lower frequency, and here the signal processing will be done at the higher frequency, that is at LNA frequency, at higher frequency. That is the basic difference. So you can, I'm not going to the details, just to tell you, if you want to go to more detail, it can be found from the literature. Okay, these are some of the multi-beam antenna arrays, multi-beam antennas. Now we will take some of the examples which are available on the literature to discuss how we can design, what are the things, what are the antenna elements we can choose to have the entire 360-degree communication. That is, so this was proposed, that was this was proposed maybe 2017 or 2018, this was proposed. It is a 28-port MIMO cube antenna for micro base station application, that is for base station applications. It is a multi-band antennas, it is dual polarized in nature. Okay, so now the cube, so it is something like a cube type structure. So cube, as you know, cube has 6 sides. So 6 sides, it will have 6 sides. So on 4 side walls, we place one type of antenna, and in the top and bottom, that is on top of bottom, we will have another type of antennas. So okay, so on 4 side walls, so we will use the end fire properties and the broadside radiations of the, let's say, the patch antenna is having the broadside radiation, and the Vivaldi antenna is having the end fire radiation. So we'll use these things. This has been used in this design to have the radiation in all the directions and to achieve the orthogonal beams. Okay, so here the problem of what was, so the problem of earlier that was blockade was there due to the feeds. It was not there, so it can be it can be used for entire 360-degree communication. Full azimuthal coverage of communication in 2 orthogonal planes can be achieved. So to start with the design, so what we have a 2 patch antenna. So these 2 patch antenna, we will have the patch antenna designated, that is port 1 and port 2, and you can have, if we excite port 1 and if we excite port 1, I will have one polarization. If I excite port 2, I will have another polarization. These two combine together to form an antenna array with 2 orthogonal polarizations. Now what we want? We want, and for antenna array, we want each antenna element should radiate individually. So there should be good isolation between the antenna element. So if the distance should be lambda by 2, but we can reduce that distance by placing some UVG tape structure, and we can bring this antenna element closer by, so that our system will be more compact. So we can have, they have put some directors to direct their beam. Means it is something like a reflector, or directors to direct their beam to have constructive interference in one direction. If you use director in this location and this location, so your beam will have some locations. It can be seen from here. So this beam with EBT director, it is something like 15 to 20, 30 degree, 15 degree away from the 90 degree here. And so this will, so as it was analyzed, this EBG based structure, so it has the band gap property for the desired frequency. So it will not allow any frequency, any electromagnetic wave from the 2 gigahertz to pass from one, that is from one port to the another. It means from antenna to the another nearby antenna. So they have used the patch, that is Vivaldi, the patch antenna and the Vivaldi antenna. So patch antenna, as I just discussed. Further, they have introduced the slots to have some frequency tuning to bring the frequency lower down. And so this was dual frequencies. It was something like 2.4 gigahertz and this for 0.4 point something. It is basically for the sub 6 gigahertz, Okay, now so to cover the 2.4 and 5 gigahertz, this one Wi-Fi band. Okay, so this was the structure. So they have used something like 3-dimensional view. I'm not going to discuss in the detail. Basic thing is that they will get the 2 bands here, and they will have the 2 different bands at 2.4 and 5 gigahertz. And each of this patch antenna has to be placed, this combination antenna array has to be placed symmetrically with respect to this one. It has to be placed at the side walls of the cube, as it was desired. It is shown here. It is shown. So it is shown. If you see here, so it was placed at the side walls of the cube. Here, and all the side walls. Okay. So now, and so it will have. So just they have plotted. So if I excite P1, so they will have one, that is they have radiation at one port. One angle. If I excite P2, they will have radiation at another plane. Means they will. If you see the E plane radiation, there is 0 degree and 90 degrees. So they will have radiations at different planes. So we can radiate in the omnidirection. Means they can have different radiations. Okay. Now for the Vivaldi antenna also, means for the where we need to place the Vivaldi antenna. So as you know, Vivaldi is a very wideband antenna. So if you want to use the same sets of your base station for the GSM and all other frequency bands, that is 3G, 4G, and 5G bands, so Vivaldi antenna can be thought of. And Vivaldi antenna having the probability of the end fire radiation, so it can be used. So it can be used for the top and the bottom of the cube. So it was designed. They have used 2 types of this one. This can be used, which will have the end fire radiation, so it will radiate in this direction, this direction, and this is the place at the top and bottom. Apart from that, so this is they have placed some another Vivaldi antenna, another type of Vivaldi antenna at the side walls to have the end fire some radiations, so that orthogonal polarization can be achieved. So it will be dual polarized antenna, dual polarized system will be there. So you can cover your entire 360 degree azimuthal coverage with the dual polarization. So this was some of the radiation characteristics. So its system will look like this. Same that whatever I have shown. This was the manufactured prototype. So your patch antenna is not visible because it is inside, and they have used some Roha cell type of foam to install the another type of. So the Vivaldi antenna is shown here. This is a 2-element Vivaldi antenna. So it has the 28 port. Four, that is four times side walls, so it will be 16 side walls. Then yeah, 16, no, that will be 4, yeah, 28 port, it will be 28 port, yeah. Okay, now, so now this was one of the antenna which was designed for the massive MIMO. Another is compact tapered slot antenna for 5G applications they have designed. So it is, they have used slot antenna. So as you know, the for the millimeter wave frequencies, the slot antenna is more, the tapered slot antenna. It is wideband in nature, so it is more preferred. So this was designed. It is something like to achieve the beam stream. So this is, so what we have, they have the, it is something like an example of active, active multi-beam antenna. So they have used different beams and they have excited with the beam forming network. Okay, so they have, just for the antenna part I will discuss. So they have this type of a tapered slot antenna, which was fed by the SIW based technology, is the SIW, and it achieves the wideband radiations. You can see the radiations. So that is WA, the width of this slot, this SIW technology controls the bandwidth. So it controls the bandwidth, so you can have the very wideband radiations. This was the property of, it was the property of your this tapered slot antenna. But how to excite it, how to connect it with the blend technology? So they have used the SIW technology for that. So they have used the SIW technology. So this was an antenna array. This was the antenna array, that is 4 antenna element array. This was single antenna element and this 4 antenna element. And this is how this is, they have designed, they have presented the this phased array antenna, that is, yeah, this topology architecture. I'm not going to discuss the details. So this will be your 1x4 antenna array. So and they have shown, if you vary the phase of this baseband module, so you can switch your beams at different angles. It is shown, if you, it is something like they have the lookup table. So if I want a beam in this direction, I should feed this one, this lookup table. If I want in another direction, I should do another one. So for 0 degree, all should be having the 0, means all the phases should be 0. For 35 degree, all should be this one, minus 65, minus 55, and 65 degree. We should feed in that way to get the desired beam. Or if I, to get the desired beam, so all the beams can be designed. Okay, now another is this meta surface lens. So this is lens based antenna, again for the dual polarized massive MIMO multi-beam systems. So as I told you earlier, this is, they have designed it for the, so this was the, so this is the lens. So what they have a patch antenna. Basic thing, antenna element is always a patch antenna or a slot antenna. So antenna. So this is why I'm showing all this. All this is a planar form. This can be used. This is used for the massive MIMO applications, for the multi-beam systems. So you have the patch antenna. It is shown here, and they are feeding patch antenna at 2 different locations to get the dual polarization. If I feed port 1, I will get one polarization. If I feed port 2, I will get another polarization. And this lens, this is metasurface based lens. So this metasurface based lens is used to, once the antenna elements are excited, so you will have different beams. Now the different beams to further to do the beam splitting and to get this one, so you will have metasurface beam. Okay, so now the lens, for lens, as I said, basically Jerusalem cross is used, and they have different layers. Why they have different layers? The reason behind is that I need zero phase shift for the basic thing. This metasurface or the lens provides the phase shift to have this multiple beams. So the beam which is pointing at center, I will have 0 phase difference, no problem. But as I move away from the center, I need different phase shift. So that was achieved by using different lens, that is Jerusalem cross. So they have used 3 layers, something like 3 layers of different size, where different size Jerusalem cross were explored, and in such a way for to have the different phase shifts for different beams. Okay, now so this they have shown for the, that is they have shown for the, that is for TE and TM waves, so they can achieve the phase shift at different frequencies. So this was their design. So if you see the at the center, this is they have used something like zonal lens design. At the center, it will have zero phase difference. As you move away from the center, you have you have something like lesser phase difference. That is, you want to provide the -8 degree phase difference, and after that means it can be substantial, it can be said. Means basic thing is that you must have something, you can think of a equipotential surface. So similarly, you can have equiangular phase variation contours are there. So you have the equiangular phase variations. Okay, so this was, as I discussed, this was patch antenna. So they have patch antenna for different polarizations, that is for horizontal and vertical polarizations. So they have realized, and after that, they have on the top of it, they have replaced this one, this metasurface lens, to use to get the frequency, to get the frequency, multi-beam characteristics at different multi-beam characteristics, and this will be at only single frequency. Okay, now this was, so till now whatever we were discussing for the it was for the base station. It can be used for base station. This system can be used for base station. This system can be used for base station. This system can be used for base station, but they are not good for the handheld mobile phone or handheld systems. So for handheld systems, what they are using, so they are, you can, as I told you earlier, you can use 16-port MIMO antenna or 8-port MIMO antenna. So you have to use MIMO antenna, and you have to judiciously place the antenna elements such a way the isolation between them should be very small. So you can see from here. So here, this is your something like diagram of a mobile antenna where the antenna elements are placed. So here you have the brown portion. We are showing an antenna for the 2G, 3G, and 4G applications, but for the 5G applications, because mobile, you will be using that mobile phone for all the for 4G, 2G, 3G, and all the applications. So here they have placed some open slot based antennas at different locations. So it will radiate at, let's say, 3.4 to 6 gigahertz, 3.4 to 3.6 gigahertz, and okay, and it can be seen also. So this, if I excite antenna 1, so all the antenna elements are having very less surface currents. Or if you excite antenna 3, all the antenna elements will have. So that proves the very good isolation between the antenna elements. Now, also question comes. So if you place your antenna, let's say if you hold your antenna will be, I mean, maybe if your this is open slot antenna, so you'll have your antenna will be shorted by your hand. So you can place in this way, that is by single hand hold or the double hand hold. So if you place by single hand, so this antenna will radiate, the antenna 1, 4, and 5 will radiate, and if you place by using the double hand, this will radiate. Okay. So this was our whatever I have talked about the multi-beam massive MIMO antenna. Now, so if you have the session is over, so we can conclude our talk. So we have proposed several multi-beam antennas, and we've given several examples of massive MIMO applications. So now the session is open for the questions. So let us take a few questions.
So any question, then you can ask to the sir here.
Yeah.
Good afternoon, sir.
Yeah.
Thank you, sir, for your very nice informative session lecture. So my question is, in this L-shaped antenna, since the dimension of this patch antenna is small, so what will be the gain of this antenna?
Which one? This antenna?
Yes, sir. The L-shaped antenna.
I don't know. I mean, I have not looked over it. That can I can provide the paper. Okay, let me check. It is there in the, so gain.
Sir, it is my just simple basic question. So that
Yeah, gain. Let me have gain.
because since the width is small, less, so gain should be less. So it will be means acceptable.
Let me check whether gain. Okay. Okay, they have not reported the gain.
Yes, sir.
Let me check if they have. No, they have not reported the gain. You can see in the. They have not reported. Yeah. Maybe.
Because many times I have seen this L-shaped structure. So it is
Yeah.
my simple means queries that if width is small,
Yeah.
that is less, then gain should be less.
Okay,
So
maybe because I have not worked upon it.
okay.
So, yeah.
Sir, my second question is that in a reflector-based passive
Yeah.
beamforming array, all antennas are working simultaneously, or they are working when we require some particular beam.
No, they are so for beamforming array. See, the passive beam antennas are working simultaneously. So that is the beauty of this one. I mean, if you excite all the ports, so they will be working simultaneously. So for all the passive beam and this passive antennas based on beamforming. So that is the basic thing, the basic difference between the active and the passive.
Okay.
You can see all the beams. Yeah.
So in passive, all antennas are working simultaneously.
Yeah. If you can see, yeah. This you can excite this. If you excite, here it's shown that if you excite port one, this is Butler matrix based passive beam arrays. If I excite port one, I will have maybe this center one. If I excite port two, I will have another beam. If I excite port three, I will have another beam. So since each of the ports are isolated to each other, we can excite all the ports, no problem.
So then what is the use of a reflector?
Okay, no, this is beam forming. Here we are not using any reflector.
I'm asking for the reflector case, sir.
Okay, reflector also it is different. Is reflector also it is working. Okay, main use of the reflector is to what if you place at this focal point, it will reflect at the means there is no interaction. Okay, so for the reflector based antennas, so here each antenna will give you one beam. Each antenna will give you one beam. So it depends on the where you place the reflector. So if you place the reflector, so you will have different beams. And so antenna elements should be placed at certain distance such that there should be good isolation.
So in this case, all are working simultaneously, or they
Yeah,
are
all are working simultaneously. Yeah, definitely.
okay.
Yeah, yeah you can see that if you feed one, two, feed three, all are working simultaneously. Because we require multi-user beam.
Yes, sir.
Yeah.
Thank
Any other questions?
I think so. There is no further questions. So please continue.
Okay. So thank you. So now just I will stop my screen. So if you want to, so I have worked since my research area is SIW. So they have used a lot of things on the SIW. Means if you see this SIW, most of the antennas they have used SIW technology for the design of massive MIMO application, multi-beam antennas. Okay, so please try to work. So if yeah, so thank you all for attending this session.
So any other query?
Nipun Kumar Mishra, are you having questions?
Yes, sir. I asked the questions.
Okay.
Yeah. Sir, one doubt is that
Yeah.
at millimeter wave frequency, Can be used aperture coupled feeding techniques, or SIW is the best?
SIW is the best.
But can be used aperture couple techniques? Because
I don't have any information. I don't have. If you use aperture couple, you will have again the isolation problem.
okay, sir.
Isolation problems that can be overcome in the SIW. SIW, we don't have any isolation problem because in SIW technology, it is a cavity bag. So each antenna element is itself isolated from the another one.
Yes, sir.
Okay. Yeah.
So any further questions from sir here? No. Okay, sir. I think there's no further question from sir here. So now I would like to close the session here. Uh, this is the 11th technical session of this online FDP here. So before we move on here, I would like to give my sincere thanks to the sir here for taking so much time and sharing his valuable input and research thoughts with all of us here. Here from his busy schedule here. And before we move on, now on the behalf of our organizing team here, would like to felicitate the sir here with a memento as a token of love. Yes, sir. We will dispatch you, sir. So this is from our senior, from the organizing
Yeah.
team.
Thank you. Thank you, Shiv.
Dispatch you.
Yeah.
Thank you, sir.
Thank you.
So with this, I'm going to close this technical session of the morning session here. So now once again, thank you very much, sir. Once again for sharing your inputs and giving such a beautiful articulated technical session with all of us. Thank you very much, sir.
Thank you. Thank you.
So all the participants who are present here, I would request them to go through the attendance sheet and complete your attendance here because it need to be marked properly. So those who have not, they need to submit the attendance. And with this, I am going to close the technical session, and we will meet again at 2:30 for the further discussion here for the next round technical session. Okay. Thank you very much.